All right, here is our setup. We have a single fringe here of height A. 4 meters away, we have a single bright fringe of 4.8 centimeters. We then cut out a same-sized hole from top to bottom. That's 250 micrometers. In the centers, it's some distance D. The actual wall is, or the board is 1 micrometer. Still 4 meters away, and now in place of that 4.8 centimeters, we have 7 bright fringes, and on the end of the 4.8 centimeters is a dark fringe. What we're looking for is the smallest possible M value of the glass. So let's get started. Let's look at the bright fringe, or not the bright fringe, the single fringe first. Geometrically, what can we figure out? Well, we know that this is a straight line. We know that this is a straight line. This forms a 90-degree angle. So we have an opposite and an adjacent. And if we have an opposite and adjacent, we have a tangent ratio. Great. So we know our adjacent is 4 meters. And our opposite is 4.8 centimeters. But because this starts at the middle of the fringe, it's only half of that. So 4.8 divided by 2 is 2.40 centimeters. We can't divide centimeters by meters. We got to convert from centimeters to meters. That's 100 centimeters in 1 meter. Notice that 2 because cancel, no units. And what we get is 2.4 over 400. That gives us 0.006. So let's say that tan theta equals 0.006. Now, there's a little quirk where if theta is really small, tan theta is basically just theta, and sine theta is also basically just theta, so we can set these equal to each other, and we get tan theta equals sine theta. Great. Sine theta, we can actually pull a lot more information about the single fringe as well. So if we just calculated tan theta to be 0.006 is equal to sine theta, and for a single fringe, sine theta is m times lambda over a. We want a, we don't know lambda, but we do know m. Because it's a single bright fringe, it's 1 times lambda over a. And to get rid of the denominators, we'll just multiply both sides by a. So we get 0.006 a is equal to lambda. We have a ratio now. All right, well, that small angle rule still applies for double slits, but also if it's both sine here, then we set them equal to each other. So we know sine for a single slit is m lambda over a. Sine for a double slit is 1/2 plus m lambda over d. You can fill in the blanks here. You know, m for a single slit is 1. We just said that. Lambda over a. And then for a double slit here, there's 0, 1, 2, 3. What we're left with is lambda over a is equal to 7 over 2 lambda over d. Now, let's multiply both sides by each other's variables. That's d on the left, a on the right, and divide by lambda. What we're left with is d equals 7 over 2, that's 3.5 a. Now we have two good ratios And we have enough information given to us to figure out what D is, and by extension, what the wavelength is. So what is that information? Information is the knowledge that this whole chunk is 250 micrometers. The midpoint, the distance between the midpoints of the two slits is D. And if it's the midpoints, that means it's half of A. So we have 250 is equal to D plus 1/2 and 2 A. So what we just get is 250 micrometers is equal to D plus A. Just found D is equal to 3A. Or 3.5A, excuse me. So we're left with is 250 micrometers is equal to 4.5A. Let's divide both sides by 4.5. What we're left with is 55.56 micrometers is equal to A. Great. Let's fill in some more blanks here. If we know what A is here, we can just plug that in for D. So D is 3.5A. That gives us 194.44. And lambda is equal to 0.006A. That just results in repeating threes. So 0.333, we'll give them a little extra micrometers. All right, well, found A, we found D, we found lambda, or wavelength. What's left? Well, so I'll just put it all together. Let's switch to blue this time. We still want the N, right? So, what can we tell just from the setup? It's the same same light, or it's the same wave, excuse me. So if it's the same wave, then delta phi is just 0. And because the central fringe is a bright fringe, we know that they're in phase. The delta phi is also 0. But it could also be 2 pi, because on the unit circle, 2 pi gets you back at the start. So we use 2 pi just because 0 is probably going to be a little tricky. 2 pi is equal to delta phi, which is phi 1 minus phi 2. Expand out of it. 2 pi is equal to k delta x minus phi, which is 0. Plus 0 minus k prime delta x, because we're getting messed with here, plus, again, 0. What we're left with there is 2 pi is equal to k, which is 2 pi over lambda, which we've already calculated out, delta x, plus 2 pi over lambda prime, delta x. What's lambda prime? Well, it's 2 pi is equal to 2 pi over lambda, delta x, plus 2 pi lambda over n, but it's flipped because it's on the denominator, delta x. Let's pull out 2 pi for lambda. So we get 2 pi is equal to 2 pi over lambda. No, excuse me. 2 pi lambda delta x is times, this is 1 plus n. Divide that over, we get lambda over delta x is equal to 1 plus n. Lambda over delta x minus 1 is equal to n. Now let's fill in the blanks. Lambda, we know to be 0.333 micrometers over delta x, which we know to be 1 micrometer. Which also means the units cancel. Minus 1 is equal to n. So what are we left with? We're left with 0.333 minus 1. We're left with oh, wait, I put a plus here, not a minus. Obviously, this is flipped off. This should all be negative. Minus n. What we're left with is negative 0.667 to negative n, which just leaves us with 0.667 equals n. That is a problem. N cannot be less than 0. So our easiest solution is just to make it negative, because positive 2 pi this way, which is what we just did, is the same as negative 2 pi this way. So we're just going to put negative 2 pi, negative 2 pi, negative 2 pi, negative 2 pi, negative 2 pi. We divide it over, it's negative lambda, negative 0.333. And then there's where we get tricky. We get negative 1.333 is equal to negative n. Thus n is equal to 1.333, which sounds a lot more correct.